Hello all. In the last sessions we were discussing about various combinational logic circuit. So we'll continue the same, and in today's session we will be discussing about two other important combinational logic circuits, which are encoders and decoders. We'll start with decoders. Okay, so decoder is basically a combinational logic circuit that change the binary information into 2 to the power of n output lines. That is, if we take n inputs, we would be producing 2 power n output lines using this particular combinational logic circuit, which is called as decoder. Okay, so basically the binary information that we want to pass, we pass that as n input lines, and depending upon these n input lines we would be able to produce 2 to the power of n bit binary coding binary information. Okay, this produced 2 to the power of n output code is equivalent to that particular binary information. Okay, so as you can see in this particular block diagram, for n inputs the decoder produces 2 to the power of n outputs. Hence, we call that particular decoder as n to 2 power n decoder. Okay, so depending upon how many bits we take in n, we have different types of decoder. Let's look into the first basic decoder. Let's take two inputs. Okay, so when I take two inputs as A0 and A1, if for two inputs I will be generating 2 to the power of n, that is 2 power 2 outputs, which I label them as Y0, Y1, Y2 and Y3. Okay, so basically we call this as 2 to 4 decoder. Okay, 2 to 4 line decoder, or in general we call it as 2 to 4 decoder. Okay, so in the line 2 to 4 decoder there are total 3 inputs. Okay, now when you look into these 3 inputs, this is enable input that acts as a switch. Okay, when you want to use this for power saving, when you want to use the switch or not, your enable input works. Okay, so basically this is an extra input. These are the two inputs for the decoder, for 2 to 4 decoder, which are A0 and A1, and we have these 4 outputs Y0, Y1, Y2, Y3. Okay, now for each combination of inputs, okay, so the output, we will be getting the output only if this enable input is 1. If you put this enable input is 0, your output will not respond to any of the combinations of inputs. Please remember this point. Your enable inputs acts as a switch. Okay, if enable input is 1 only, your output will be responding to the inputs. If enable input is 0, no matter what you change in the inputs, your output will not be responded. Okay, so this is the block diagram for 2 to 4 decoder. Okay, now when you look into the truth table, okay, when you look into the truth table, here I am taking enable input. Along with that, I am taking two inputs A0, A1, and these are the outputs Y0, Y1, Y2, Y3. Okay, now when you look into this enable input, if it is 0, if enable input is 0, no matter what, XX represents all combinations of A and 1, okay, A0 and A1. So no matter what you give in the output, none of the what you give in the inputs, none of the outputs will be activated. Okay, now only if enable input is activated, only if enable input is 1, for 0, 0 combination of inputs, Y0 will be activated. For 0, 1 combination of inputs, Y1 will be activated. For 1, 0 combination of inputs, Y2 will be activated. For 1, 1 combination of inputs, Y3 will be activated. Did you all get this? For enable input 0, irrespective of what combination of input you give, none of the output will be activated. For enable input as 1, depending on how you change your inputs, one of the output will be activated. Okay, so from this particular truth table, these are the logic expressions that I write. So for Y3, I have only A0 and A1. Okay, so E with A0 and A1. For Y2, it is A1 A0 bar. Okay, for Y1, it is A1 bar and A0, and for Y0, sorry, yeah, for Y0 it is A1 bar and A0 bar. Okay, now that is the truth table. This is the logic expression, and using this logic expression, do I have to go for K-map here? No, because I don't have many possibilities here. So I am not going for K-map. I am directly getting the reduced expression because only one of the output is high for all the given outputs. Okay, now using the logic expressions given above, I am designing my logic circuit. Okay, so Y0, Y1, Y2, Y3 are the outputs here. For Y0, it is enable input. E, I am taking it as common. Okay, so for Y0, it is A1 bar, A0 bar. So this is your bar circuit. Okay, this is the inverter. So for Y0 it is output of both of them. Okay, similarly for Y1, Y2 and Y3 I am designing this particular logic circuit. Okay, so always remember, whenever you're dealing with any of the combinational logic circuit, okay, you explain what does that logic circuit do, the block diagram of it, the truth table for the given logic circuit, the logic expression, apply K-maps wherever required. For this case I don't need, so I have given the logic expression directly, and from the given logic expression you have to construct your logic circuit. Okay, now this is a 2 to 4 decoder. Okay, now let me take 3 inputs and design 3 to 8 line decoder. So when I take 3 inputs, as I told you, for decoder, for n inputs we will have 2 power n combination. So when I take 3 inputs we will have 2 power 3, that is 8 combination, hence we call this circuit as 3 to 8 decoder. Okay, so basically as we are decoding 8 different outputs, this is called as binary to octal decoder. Okay, so in 3 to 8 decoder there are totally 8 outputs starting with Y0 to Y7, and there are 3 inputs A0, A1, A2. Okay, so the reason why I didn't include is you can put enable, that is up to you. Okay, so the circuit has enable input just like 2 to 4 decoder also, and this is your simple block diagram. Okay, now similar to what I have done in 2 to 4 decoder, I am doing the same thing here. So this is the truth table for 3 to 8 decoder. I am putting the enable input here, 3 inputs A0, A1, A2, 8 outputs Y0 to Y7. Okay, so if your enable input is 0, despite of or in spite of what you take in A0, A1, A2, the output will always be 0. None of the outputs will respond to the inputs because your enable input is 0. Okay, so only if enable input is 1, for all 8 combinations of A0, A1, A2, that is 0, 0, 0 to 1, 1, 1, one of the output will be high. If it is 0, 0, 0, Y0 will be high, 0, 0, 1, Y1 will be high, 0, 1, 0, Y2, 1, 1, 1, Y7. Okay, so from the given truth table, these are the logic expressions. Using these logic expressions, we have designed the combinational logic circuit. Okay, as you can see, Y0 is A0 bar, A1 bar, A2 bar. Okay, so Y0 is A0 bar, A0 bar, A1 bar, A2 bar. So I have taken A line, A0 line, A1 line, A1 bar line, A2 line, A2 bar line with an inverter. So wherever the required points, so Y1 is A0, A1 bar, A2 bar. So Y1 is A0, Y1 is A0, A1 bar, A2 bar. Okay, you can also add enable input as common to all the logic gates. Okay, so this is the logic diagram for 3 to 8 decoder. Okay, now let's look into another advanced decoder which is called as 4 to 16 line decoder. Okay, for 4 inputs we will be having 2 power 4 outputs, that is 16 line decoder. Okay, now in this 4 to 16 line decoder there are total 16 outputs, Y0 to Y15. Okay, sorry, it is Y0 to Y15, and we will have 4 inputs A0 to A3. Okay, now this 4 to 16 line decoder can be constructed using 2 to 4 decoders or 3 to 8 decoders, that is up to you. Okay, now I don't want to design my decoder circuit from the scratch. Okay, I want to design decoder circuit from existing decoders. Okay, now as you can see the truth table here, I have 4 inputs, right? 0, A0, A1, A2, A3. Okay, now look into this. Till this particular point, A0, A1, A2 are 0, 0, 0 to 1, 1, 1. From here again it is A 0, 0, 0 to 1, 1, 1. Just that A3 bit is 1, here A3 bit is 0. Okay, so what we do here is, I take a 3 to 8 decoder. Okay, I add another inverter to it. Okay, so that is from Y0 to Y1 it is 0, A3 is 0. Okay, so here Y0 to Y7 I take an inverter. Okay, look at this, A3 bit I am taking an inverter, and this would be 1 for Y8 to Y15, and that would be 0 by connecting an inverter to this particular thing. Okay, so A3 bit is 1 for A3 bit is 1 for Y8 to Y15. From Y0 to Y7 A3 bit would be 0, and here it is 1. So that is the reason A0, A1, A2, A3 I am taking them directly. So 3 to 8 decoder and 3 to 8 decoder will have A0, A1, A2 as common pins. A3 is 0 for Y0 to Y7, A3 is 1 for Y8 to Y7. Okay, so this is how I design 4 to 16 decoder using 3 to 8 decoders. Okay. Okay, so from the given truth table, these are my logic expressions, and you can also design it this way. Okay, you can also design your 4 to 16 decoder using the normal methodology that we have seen. From each logic expression, Y0 to Y15 from A, B, C inputs along with the enable input that we are taking it as fourth input. Okay, so you can do it this way as well. Okay, so the next topic is the next combinational logic circuit, which is encoders. Okay, so the combinational logic circuits that changes the binary information to n input lines, okay, from 2 power n to n, that is the reverse functionality of decoder is your encoder circuit. In decoder circuits we have n inputs and 2 power n outputs, whereas in encoders we have n outputs for 2 power n inputs. Okay, so the binary information is usually passed in the form of 2 power n input lines, and for those 2 power n input lines the n bit binary code will be decoded. That is, encoder performs exactly the reverse operation of decoder, and this is a simple block diagram of that. 2 power n input lines will be there, for which encoder will produce 2 power n output lines. Okay, so first we'll start with 4 to 2 line encoder. Okay, so in 4 to 2 line encoder we will have 4 inputs which are labeled here as Y0, Y1, Y2, Y3, and for these 4 inputs we have 2 outputs which are A0 and A1. Okay, now these 4 input lines and one input, sorry, in these 4 input lines, one of the input line is set to be activated at a time to get this particular respective binary code in the output. Okay, now let's check the truth table of this. As you can see, one of the input lines, that is 1 0 0 0, for this combination my output will be 0 0. If Y2 is activated, my output will be 0 1. If Y1 is activated, my output is 1 0. If Y0 is activated, my output would be 1 and 1. Okay, now using that particular logic circuit I have given this expression. So A0 I have 2 times 1 for A0 case, I have 2 times 1 for A1 case. So for which I have written as A1 is equal to A0 is equal to Y3 plus Y1 and A1 is equal to Y3 plus Y2. So using this logic expression, this is the logic circuit that we have designed. Okay, so this particular logic circuit is for 2 to 4 line. Okay, this particular logic circuit is for 4 to 2 line encoder, that is 4 inputs and 2 outputs. Okay, similarly we'll look into 8 to 3 line encoder. Okay, so here in 8 to 3 line encoder we have 8 inputs which are Y0 to Y7, and we have 3 outputs which are A0 to A2. As we have these 8 inputs, we call it as octal. As they are generating the binary output, we call it as octal to binary encoder. Okay, so here in these 8 output lines or 8 input lines, Y0 to Y7, one of the input line will be set to true. Okay, only one of the input line will be set to true. Based on that, the respective binary code will be appearing at the output side, like what we have seen for 4 to 2 line. Okay, now look at this. Y0 to Y7 are the inputs. When Y0 is high, it is 0 0 0. Where Y1 is high, one of the inputs only will be highlighted here in encoder. Okay, so when Y1 is high, it is 0 0 1. When Y2 is high, it is 0 1 0. When Y3 high, 0 1 1. When Y4 is high, 1 0 0. For Y5, it is 1 0 1. For Y6, it is 1 1 0. And for Y7, it is 1 1 1. Okay, so depending upon how did we generate these outputs, the logic expressions are given here in the truth table. Okay, from the truth table these are the logic expressions, and from the logic expressions we have constructed this logic circuit. Okay, so for Y1, Y2, Y3, Y4, Y5, Y6, Y7 we have these outputs A0, A1 and A2. Okay, now When we talk about encoders, we will also talk about another encoder which is called as 10 to 4 line encoder, that is called as decimal to BCD encoder, encoding decimal to BCD numbers. Okay. So, here in this case we have 10 inputs starting from Y0 to Y9, and we have 4 outputs starting from A0 to A3. Okay. Now, in these 10 input lines, one of the input lines will be set. Always remember, for encoders, only one of the input line should be set for the output to respond. Okay. We will discuss about what if two line inputs are set in the next example. Okay. Now, if one of the input line is set to true at a given time, we get the corresponding BCD code in the output side. So, for decimal input, we are getting the BCD output. Okay. So, this is the block diagram for the same, and this is the truth table. As you can see in the truth table, I have the input starting from Y0 to Y9, and I have input 0, A0, A1, A2, A3 as the outputs. Okay. So, for each input line I have my binary representation and the corresponding outputs. Using this truth table, we have derived the logic expressions for A0, A1, A2 and A3. Okay. Now, using this logic expressions, this is the logic circuit that we design for decimal to binary adder, taking decimal numbers 0 to 9 and producing the equivalent binary digit of that particular BCD number of that particular number. Okay. Now, the next circuit or the last combinational logic circuit for the day is priority encoder. Okay. Now, this case is all about what if not only one of the input is high for the encoders. What if two inputs are high in the encoder side for the encoder? Okay. So, in the priority encoder, we are talking about 4 to 2 line priority encoder, which is 4 inputs Y0, Y1, Y2 and Y3. Okay. Basically, there are 4 inputs and we have 2 outputs A0, A1. Along with this particular thing, we also have another output which is called as V. Okay. Now, here when you look into this, if none of the inputs are activated, okay, so A0, A1 will be unknown. A0, A1 will be unknown, for which the priority is 0. I am not putting any priority. Okay. Now, when you look into this particular case where only Y0 is high, my output would be 0, 0. Okay. If Y1 is high, look at this case, if Y1 is high and Y0 is unknown, that is, if Y1 is high and Y0 is 0 or 1, okay, here when I take Y0 also as 1, what would happen? Okay, the priority would be given to Y1, hence the output would be 0, 1 only. Okay, if Y1 is high, if you have Y0 also has high, the output would be considered as Y1. The priority will be given to the highest number. Okay. So, that is the reason we are putting it as X here. This X represents either 0 or 1. So, even if it is 1, that is, if two inputs are 1, the priority will be given for Y1, hence the output would be 0, 1. Okay. Next, if Y2 is 1 and if Y0, Y1 are XX, that is, XX can be 0, 0, 0, 1, 1, 0 or 1, 1. Okay. So, despite of having any numbers in Y1 and Y0, if your Y2 is high, your output would be 1, 0 only. That is two binary representation. Next, similarly, if Y3 is high, you might have anything in Y2, Y0, Y1, 0, 0, 0 to 1, 1, 1 combinations. The output would be always 1 and 1. This is called as your priority encoder. So, here the priority encoder says, if you have Y0, Y1 as high, the output would be of Y1. Okay. If you have Y0, Y1, Y2 as high, the priority would be given to Y2. The output would be of Y2. If you have all 4 ones, the output would be 1, 1, because the priority will be given to Y3. Okay. So, this is the truth table of the priority encoder. Based on the truth table, we will have, see, we have multiple different cases, right. So, when you have this 1 and 1 combination, we have multiple cases. So, hence I have gone for K-maps. So, from K-maps, we have generated the outputs for A0 and A1 using this particular A0 and A1. This is the circuit diagram, logic diagram. As you let's see this. A1 is Y3 plus Y2. Okay, A1 is Y3 plus Y2, and then A naught is Y3 plus Y2 into Y1. A naught is Y3 plus A naught is Y3 plus Y2 bar into Y1. Okay. Now this V, when you look into this particular V, it is 0 for all zeros and 1 for the remaining cases. Okay. So 0 for all that and 1 for the remaining cases. Okay. So this is all about your priority encoder. Okay. So basically what are the uses of these encoders? Okay, so we use these encoders to convert decimal number into binary number, and main objective is to perform the binary operations such as addition, subtraction, multiplication, division. All these things can be done by using your encoders. Okay, so decoders and encoders are the most important combinational logic circuits which we actually use for decoding or encoding your binary information into the decimal lines or anything. Thank you.